What if an object existed, with gravity so strong that not even light could escape? Imagine a cosmic trapdoor, a point of no return. Out in the vast, silent theater of space, such objects are not just science fiction. They are real. We see their influence everywhere we look, written in the motion of stars and the shape of entire galaxies. These are places where the fabric of the universe itself is pushed to its absolute breaking point. They are the ultimate expression of gravity, an invisible force that governs the cosmos, but taken to an unimaginable extreme. The universe is filled with wonders, from the fiery birth of stars to the stately dance of galaxies, but none are more profound or more perplexing than this. We are about to journey to the edge of reality. Our voyage will take us through curtains of interstellar gas and past the brilliant explosions of dying stars. We will witness the very structure of space and time bend, twist, and tear. This is a story that begins with a simple prediction, a curious thought scribbled in the equations of Albert Einstein a century ago. It was a prediction so strange, so seemingly impossible, that even Einstein himself doubted its existence. Yet the universe has proven to be stranger than we ever dared to imagine. These objects, once a mere phantom of mathematics, have been found. They are out there, waiting in the dark. But these cosmic titans are not the ravenous vacuum cleaners of popular imagination, indiscriminately sucking up everything in their path. The truth is far more elegant and far more terrifying. A black hole is a region of space-time that has collapsed under its own immense weight. It is a place where gravity has become so overwhelmingly powerful that the rules of the universe as we know them no longer apply. It is a distortion of reality itself, a scar on the cosmos. To understand them is to confront the limits of our own knowledge and to ask fundamental questions about the nature of existence. This journey will take us deep into the heart of these enigmatic objects. We will explore their violent births in the catastrophic deaths of giant stars. We will see how they grow to become the supermassive anchors of galaxies like our own Milky Way. We will learn how scientists, through incredible ingenuity, can detect these invisible monsters and even capture their image from across unimaginable distances. We will travel to the very edge, the event horizon, a boundary from which there is no escape, and we will peer into the darkness, asking the ultimate question: what lies inside? Every story has a beginning. For a black hole, that story begins long before its dark and mysterious existence, in a place of immense light and creation, a stellar nursery. Across the cosmos, vast clouds of cold gas, dust, some stretching for hundreds of light years, slowly churn. Over millions of years, gravity, the patient sculptor of the universe, begins its work. It gently pulls these materials together into dense, swirling knots. As these clumps grow more massive, the pressure and temperature at their cores begin to skyrocket, reaching millions of degrees. It is here, under these extreme conditions, that a star is born. This fiery genesis marks the start of a lifelong battle against the relentless pull of its own gravity. At the heart of a young star, a process of cosmic alchemy commences: nuclear fusion. The intense heat and pressure are so great that they force hydrogen atoms, the simplest and most abundant element in the universe, to fuse together, forming helium. This reaction unleashes a tremendous amount of energy, which radiates outward from the star's core. This outward push of energy provides the crucial counterforce to gravity's inward crush. For millions, or even billions of years, the star exists in a state of perfect equilibrium, a delicate balance between the explosive force of fusion pushing out and the immense force of gravity pulling in. It is a stable, shining beacon in the cosmic dark. But the life of a star is a story of constant transformation. As the hydrogen fuel in its core is depleted, The star begins to fuse helium into heavier elements like carbon, oxygen. This process continues, with the star's core becoming a layered, onion-like structure, forging progressively heavier elements: neon, magnesium, silicon. Each new stage of fusion requires even higher temperatures and pressures, and each stage burns through its fuel more quickly than the last. The star swells dramatically, its outer layers cooling and expanding to become a red giant or red supergiant. These titans are so vast that if one were placed where our Sun is, it could engulf the orbit of Jupiter. This celestial furnace is responsible for creating nearly all the heavy elements that make up our world. The carbon in our cells, the oxygen we breathe, the silicon in the rocks beneath our feet, all were forged inside the fiery hearts of stars that lived and died long before our Sun was born. In this sense, we are all made of stardust. The life of a star is not just a battle against gravity, it is the universe's primary engine of creation. But for the most massive of these stellar giants, their final act will not be one of creation, but of ultimate collapse. Their destiny is to become something far stranger. Long before the first black hole was ever discovered, its ghost haunted the pages of a revolutionary new theory. To understand where this idea came from, we must go back to the early 20th century and revisit our understanding of the most familiar force in the universe: gravity. For more than 200 years, Isaac Newton's law of universal gravitation reigned supreme. It described gravity as an invisible force, a mysterious action at a distance. This view worked perfectly for predicting the fall of an apple. It also predicted the orbit of a planet. But a brilliant young patent clerk named Albert Einstein was about to change everything. He was deeply troubled by Newton's instantaneous force, which seemed to violate his own new theory of special relativity. Einstein spent a decade wrestling with this problem, embarking on a profound intellectual journey. He realized that gravity was not a force at all. Instead, he proposed something far more profound and mind-bending. Gravity, he argued, is a consequence of the curvature of space-time. In 1915, he published his masterpiece, The General Theory of Relativity. This theory reimagined the universe as a four-dimensional fabric, the three dimensions of space and the one dimension of time. According to Einstein, massive objects like stars and planets don't pull on other objects with a mysterious force. Instead, they warp and bend the very fabric of space-time around them, like a heavy bowling ball placed on a stretched rubber sheet. Marbles rolling and curving around the sagging sheet. This new vision of gravity was elegant and powerful. Objects in motion, like planets orbiting a star, are simply following the straightest possible path through this curved, four-dimensional landscape. What we perceive as the force of gravity is just the feeling of moving along these curves in space-time. This was not just a philosophical shift. It made concrete, testable predictions that differed slightly from Newton's laws. It predicted that the light from distant stars should bend as it passes by a massive object like the Sun. It also explained a tiny, persistent wobble in the orbit of the planet Mercury that Newton's theory could not account for. Einstein's theory was a triumph of human intellect, a complete rewriting of our understanding of the cosmos. It transformed gravity from a simple force into the dynamic geometry of the universe itself. The equations of general relativity described how mass and energy tell space-time how to curve, and how curved space-time tells matter how to move. But hidden deep within these elegant equations was a prediction so bizarre, so extreme, that it would take decades for the scientific community to accept it. The theory not only described the gentle curves around stars and planets, but also predicted the possibility of places where space-time could break completely. The point of no return. The Schwarzschild radius defines a true physical boundary, a one-way membrane in space-time, the event horizon. It is not a physical surface you could touch. It is a purely geometric border in space. For an object the mass of our Sun, this radius is about 3 kilometers. For the Earth, it is a mere 9 millimeters. Compress the Sun to the size of a small town, compress the Earth to the size of a marble, and you'd create a black hole. Once an object's mass sits inside that critical radius, space-time curvature becomes extreme. All possible paths for matter and light then lead inward toward the singularity. Crossing the event horizon is irreversible. From the falling astronaut's view, nothing dramatic happens at the crossing. There is no wall. There is no signpost. They would simply drift across an invisible line. But from that moment, their fate is sealed. Space-time itself flows inward like a waterfall, faster than light. Escape would require outrunning light. Impossible. Inside the horizon, the direction to the singularity becomes the future. All timelines point to the center. A distant observer sees something different. Gravitational time dilation makes the astronaut's clock tick slower and slower. Their movements appear to decelerate. The light they send is stretched and reddened, gravitational redshift. To outside eyes, the astronaut seems to slow, dim, and freeze at the horizon, their image fading into oblivion over infinite time. They are never observed to cross. They encounter a far more violent effect of extreme gravity, tidal forces. On Earth, the Moon's gravity pulls slightly more on the side facing it and less on the far side. This difference makes the oceans bulge, creating tides. Near a black hole, the same principle is amplified to a terrifying degree. The pull on the part of the astronaut closer to the singularity is exponentially stronger than the pull on the part farther away. That difference across their body creates an overwhelming stretching effect. For a smaller, stellar mass black hole, only a few times the Sun's mass, tidal forces are immense even outside the horizon. An astronaut falling feet first would feel their feet pulled much more than their head. The stretching force grows rapidly, pulling them apart beyond molecular bonds. This gruesome process is grimly nicknamed spaghettification. The astronaut, their ship, elongate into a thin stream of atoms, are stretched, then squeezed into a river of plasma, funneled toward the center. All the matter that has ever fallen into the black hole, including the remnants of our unfortunate astronaut, continues on its unstoppable journey to the very center. According to Einstein's theory of general relativity, all of this mass is crushed into a single point of zero volume and infinite density. This is the singularity. It is a place where the curvature of space-time becomes infinite, and all the known laws of physics break down completely. Our most successful theory of gravity simply ceases to make sense. It predicts a physical infinity, which is a clear signal to physicists that the theory is incomplete. The singularity represents the ultimate frontier of our knowledge, a place where our understanding of reality hits a wall. What is it really? Is it a point of infinite density, as general relativity suggests? Or is it something else entirely? Something that a more fundamental theory would describe? We simply do not know. To truly understand the singularity, we need a new theory, one that can unite the two great pillars of modern physics, Einstein's general relativity and quantum mechanics. The search for this unified theory, often called quantum gravity, is one of the biggest challenges in science today. For now, it remains an enigma, wrapped in a horizon at the heart of darkness. For a long time, black holes were thought to be rare and exotic objects, the lonely remnants of colossal stars. But as our observational power grew, astronomers began to notice something strange. When they looked at the centers of distant, massive galaxies, they saw stars, gas clouds, moving at incredible speeds, orbiting an unseen central point. The velocities were so high that the only explanation was a gravitational anchor of immense power, an object with a mass not of a few suns, but of millions of suns, or even billions of suns. These observations were the first clues that a new class of black hole existed, the supermassive black hole. They were not just anomalies, they appeared to be a fundamental component of galaxies themselves. Unlike their stellar mass cousins, the origin of these giants is a profound puzzle. A single star collapsing cannot create an object so massive. One leading idea: they began as smaller seed black holes in the early universe, which then grew over billions of years. These seeds might be remnants of the very first generation of stars. Another possibility: direct collapse of enormous clouds of gas at the dawn of galaxy formation. Whatever their origin, they grew voraciously, merging with other black holes, accreting vast amounts of gas, accreting stars from dense galactic environments. Today, nearly every large galaxy, including our Milky Way, harbors one of these behemoths at its core. Their masses are staggering. The supermassive black hole at Andromeda's center weighs over 100 million solar masses. M87's black hole, the first ever imaged, is 6.5 billion times the Sun's mass. If placed in our solar system, its event horizon would extend far beyond Pluto's orbit. These objects are cosmic monsters that dwarf anything nearby, true giants lurking in the galactic dark. Their discovery changed our understanding of the cosmos. They were no longer endpoints of stellar evolution, but central players in the grand drama of galactic evolution. Their immense gravity governs stars in the galactic core, creating a dense, frenetic stellar neighborhood. But their influence extends far beyond gravity. These sleeping giants can awaken, transforming into the most luminous and powerful objects in the universe, able to shape the destiny of the galaxy they call home. Black holes, by their very definition, are invisible. They are points of infinite gravity from which no light can escape, making direct observation impossible. So how do we know they are there? How do we hunt for these cosmic ghosts? The answer lies in observing their profound effects on the space and matter around them. Scientists are cosmic detectives, searching for clues left behind by these invisible giants. One of the earliest methods was to look for specific types of binary star systems. Imagine two stars orbiting each other, but you can only see one. If the visible star is being pulled into a rapid, tight orbit by an unseen companion, and if that companion is too massive to be a normal star or a neutron star, a black hole becomes the prime suspect. This suspicion becomes near certainty when the system emits powerful X-rays. As the visible star gets too close to its invisible partner, the black hole's gravity can siphon gas from the star's outer layers. This stolen material doesn't fall straight in. It forms a swirling, superheated accretion disk around the black hole. Just like with their supermassive cousins, intense friction in this disk heats the gas to millions of degrees, causing it to glow brightly, not in visible light but in high-energy X-rays. Telescopes in orbit around Earth can detect this X-ray signature, pointing to a location where matter is being heated to extreme temperatures before vanishing forever. The combination of orbital motion and X-ray emission provides powerful, albeit indirect, evidence for a stellar mass black hole. Another method uses gravity's ability to bend light, gravitational lensing. As predicted by Einstein, a massive object warps space-time, and that curvature can bend the path of light from a distant object. When a black hole passes directly in front of a background star, its gravity acts like a lens, focusing and amplifying the star's light. The background star temporarily brightens in a specific, predictable way. This effect, known as microlensing, is rare and requires monitoring millions of stars for tiny, fleeting brightness changes. When detected, it reveals isolated black holes with no accretion disk, truly invisible, found only by their gravitational fingerprint. At galactic centers, the telltale sign is the motion of the stars themselves. As we saw in the Milky Way, astronomers track the orbits of stars whipping around a dark, central point. By measuring the speed and shape of these orbits, they calculate the mass of the central object with astonishing precision. When that mass is millions of times our Sun, or billions of times our Sun, all crammed into a tiny volume of space, nothing else fits the description. Observing what we cannot see by its influence on what we can has allowed us to build a comprehensive census of black holes, confirming their existence long before we could ever hope to see one directly. Even with all these methods, the ultimate prize remained: to capture a direct image of a black hole's silhouette. The challenge was immense. Even the nearest supermassive black holes are incredibly far away, making them appear smaller in the sky than a donut on the surface of the moon. No single telescope on Earth was powerful enough to resolve such a tiny object. To do it would require a telescope with a mirror the size of the entire planet. So, an international collaboration of scientists decided to build one. They created the Event Horizon Telescope, or EHT, a global network of radio telescopes scattered across the globe. Mountains of Chile, frozen plains of Antarctica, all synchronized by atomic clocks. Using very long baseline interferometry, the EHT combines data from these telescopes into a virtual Earth-sized observatory. For several nights in April 2017, all the telescopes swiveled to stare at two targets, Sagittarius A and M87, 55 million light-years away. The telescopes collected petabytes of data, stored on hundreds of hard drives, physically flown to processing centers. Weaving that data into an image was a monumental computational challenge that took 2 years. The target in M87 was a true monster, 6.5 billion solar masses. Its immense size and active accretion disk made it ideal for imaging. After years of painstaking work by hundreds of scientists, the moment of truth arrived. On April 10, 2019, coordinated press conferences worldwide, the EHT unveiled the result. For the first time, humanity could see the unseeable. The image showed a bright glowing ring, superheated plasma orbiting a perfect circle of darkness. This dark region was the black hole's shadow, where light is captured, a visual confirmation of the event horizon. The image vindicated Einstein's theories. Size and shape matched general relativity almost perfectly. It was blurry and imperfect, but it was real. It represented human collaboration, ingenuity, relentless curiosity. Black holes moved from equations and artists' impressions to observable reality. We had stared into the abyss, into the maw of a cosmic monster 55 million light-years away, and captured its portrait. It was a profound, emotional moment, a testament to collective achievement and to exploring the universe's deepest mysteries. For decades, the laws of physics seemed clear. What falls into a black hole stays in a black hole. They were seen as eternal prisons of matter and information, cosmic dead ends. But in the 1970s, the brilliant physicist Stephen Hawking decided to challenge this idea. He embarked on a thought experiment to combine the two great pillars of modern physics: Einstein's general relativity, the law of the large, and quantum mechanics, the law of the very small. Hawking wanted to understand what would happen to quantum particles at the edge of a black hole, right at the event horizon. His calculations led to a conclusion so shocking it overturned everything we thought we knew. According to quantum mechanics, empty space is not truly empty. It is a roiling, bubbling sea of virtual particles that pop into existence as matter-antimatter pairs, exist for a fleeting moment, and then annihilate each other. Hawking theorized that if one of these pairs appeared right at the edge of an event horizon, a strange thing could happen. One particle falls into the black hole while its partner escapes into space. To a distant observer, it would look as though the black hole itself was emitting a particle. The escaping particle has positive energy, which must be balanced. It gets this energy from the black hole itself, effectively stealing a tiny amount of the black hole's mass. This steady trickle of escaping particles became known as Hawking radiation. It is an incredibly slow process, but the implication is profound. Black holes are not completely black. They have a faint glow, and more importantly, they leak. Because they are constantly losing mass through this process, Hawking realized that Over unimaginably long timescales, black holes must evaporate. Black holes are not eternal after all. This revelation created a new, deeper puzzle known as the information paradox. A fundamental principle of physics states that information cannot be destroyed. The information about what an object is, its specific arrangement of atoms, is always preserved, even if the object is burned or smashed. But if a black hole evaporates by emitting random thermal radiation, what happens to the information about all the things that fell into it? Is the unique information about a star or an astronaut who fell in simply erased from the universe forever? This would violate the laws of quantum mechanics. It's a paradox that pits our two best theories of the universe against each other, and physicists are still debating the answer today. The extreme warping of space-time by a black hole has naturally led to one of the most tantalizing ideas in science and science fiction. Could they be gateways? Could a black hole be a portal, a shortcut through the vast distances of the cosmos, or even a bridge to another universe? This idea has a surprising basis in established physics. Einstein and his colleague Nathan Rosen realized that general relativity allows for bridges connecting two different points in spacetime, more commonly known as wormholes. The concept is alluring. An astronaut could enter the mouth of the wormhole, the black hole, and emerge almost instantaneously at another mouth, billions of light-years away. It would be the ultimate form of travel. The problem is, these simple wormholes are not stable. The classic Einstein-Rosen bridge is profoundly unstable. It would collapse almost instantly, pinching off faster than even light could traverse them. To keep a wormhole open would require a form of exotic matter, negative mass or negative energy density. This material has never been observed and may be impossible to create. So while the idea is compelling, we must distinguish established science from speculation. As of today, there is zero observational evidence that wormholes exist. For now, a black hole is not a doorway, it is a one-way trip to oblivion. Our journey to the edge of reality has revealed as many questions as it has answered. Black holes are the ultimate cosmic laboratories, pushing our theories to their breaking point and exposing the deep cracks in our understanding of the universe. At the forefront is the mystery of the singularity. What is really at the center of a black hole? Is it a point of infinite density as general relativity predicts? Or is it something else, something stranger, described by a new theory of quantum gravity? The information paradox also remains a central puzzle. Does information truly get destroyed when a black hole evaporates? Or is it somehow encoded in the outgoing radiation, scrambled but not lost? To find the answers, we are building bigger and better tools. The Event Horizon Telescope is expanding. New gravitational wave observatories are being planned on the ground and in space, like the Laser Interferometer Space Antenna, or LISA. These next-generation detectors will be able to hear the gentle hum of supermassive black holes merging across the universe, providing a new soundtrack to cosmic history. These tools will allow us to probe the dark universe as never before. Do black holes hold the key to understanding dark matter? Do black holes hold the key to understanding dark energy? How exactly did the first supermassive black holes form? Can we ever prove or disprove the existence of wormholes? These are the questions that will drive the next generation of astronomers, physicists, and explorers. Black holes are not just objects to be studied. They are signposts pointing toward a deeper, more complete description of the cosmos. The darkness is calling, and it is filled with the promise of discovery. Our journey has taken us from the fiery nurseries of stars to the silent, invisible precipice of the event horizon. The story of black holes is a story of human curiosity pushing against the boundaries of the known universe. They represent the ultimate triumph of gravity, a force so powerful it can bend light, warp time, and tear the very fabric of reality itself. They are nature's ultimate laboratories, places where the fundamental laws of physics are pushed to their absolute limits and beyond. They are the battleground where our two most successful theories collide, hinting at a deeper, more unified theory that still awaits discovery. To study them is to ask the most profound questions we can pose. What is the nature of reality? Where did the universe come from? And what is our place within this vast, mysterious cosmos? The quest to understand these cosmic mysteries has only just begun. As our technology advances and our theories evolve, these dark, silent objects may ultimately reveal the deepest and most fundamental truths about the universe. They are not merely objects in the universe. They are laboratories where the laws of nature are pushed to their limits. As our technology advances and our theories evolve, these cosmic mysteries may ultimately reveal the deepest truths about the universe and our place within it.